Hello! In this video, we're going to prove the following theorem. X over the square root of 1 plus x squared is less than arctangent of x, which is less than x, for all positive real numbers x. Now, first of all, let's remind ourselves of our definition of the arctangent function. Let x be any real number and consider the following sequence. Now, when we say for all n, this just means for all integers n greater than or equal to 0. Now, it turns out we have shown that the limit of this sequence converges to 0. And we also showed that the sequence to the n xn converges. And we defined the value that this sequence converges to be the arctangent of x. And the way that we proved this sequence converges was we split it up in two cases. In the case x equals 0, we saw that this sequence was just a constant sequence of zeros. So the sequence converges to 0, and so in this case, we have that the arctangent of 0 is equal to 0. In the case x is greater than 0, we found that all of the xn's are greater than 0, and we saw that the sequence to the n xn is a decreasing sequence bounded below by 0. In the case x less than 0, we found that all the xn's are less than 0. And we had that 2 to the n xn is an increasing sequence bounded above by 0. So what we see here is, in the case x equals 0, we have that arctangent of 0 is 0. But in the case x is greater than 0, what can we say about the arctangent of x? Well, in the case x is greater than 0, we found that 2 to the n xn is greater than 0 for all n. By properties of limits, that implies the limit of 2 to the n xn is greater than or equal to 0. In other words, arctangent of x is greater than or equal to 0. Similarly, in the case x less than 0, we found that 2 to the n xn is less than 0 for all n. And by properties of limits, that implies the limit of 2 to the n xn is less than or equal to 0. In other words, arctangent of x is less than or equal to 0. Right, so we currently know that this is true. But the claim is that we can also show that these are strict inequalities. And these two claims will immediately follow from this theorem. So then, how do we actually prove this theorem? Well, the idea is we are going to consider another sequence that will also converge to the arctangent of x. And that sequence is the following. This sequence will also converge to the arctangent of x, because we can show that using properties of limits. Because we know that the sequence in the numerator will converge to arctangent of x, the sequence in the denominator will converge to 1. Because xn converges to 0, therefore xn squared converges to 0, therefore 1 plus xn squared converges to 1, therefore square root of 1 plus xn squared converges to 1. And so, by the division property of limits, this guy converges to arctangent of x over 1. Which is equal to arctangent of x. Now remember, we saw that in the sequence 2 to the n xn, we have, depending on what x is, the sequence 2 to the n xn will exhibit different behavior. The same thing is also going to be true for this sequence, right? This sequence will exhibit different behavior depending on what x is. The claim is, if x is greater than 0, then this sequence is an increasing sequence. And if x is less than 0, then this sequence is a decreasing sequence. So it's going to exhibit opposite behavior as 2 to the n xn. And to prove the behavior of this sequence, the following fact will be useful. It turns out this equality will be true. To prove that, well, again, we're working with an arbitrary real number x, and we're working with an arbitrary integer n greater than or equal to 0. with this arbitrary real number x, we're considering this sequence, and we're considering some arbitrary integer n greater than or equal 0. The claim is that this equality is true. Now, one way that you could prove this is you could take the right-hand side, substitute the xn plus 1s with what they are by definition, and then just simplify it down to this. That's one way to do it. Another way to do it is using complex numbers. So, we're going to first note, by definition, xn plus 1 is equal to this. And then, if we divide both the numerator and denominator by square root of 1 plus xn squared, we get this. So now, we're going to use the following fact about complex numbers. Suppose alpha plus beta I is a complex number with magnitude 1 whose real part is not equal to negative 1. Then alpha plus beta I is equal to this. So, applying this fact, we are going to take alpha plus beta I to be the following complex number. We're taking alpha plus beta I to be this complex number. Well, with this choice of alpha plus beta I, certainly the magnitude of it is equal to 1. And certainly the real part is not equal to negative 1. So with this choice of alpha plus beta I, this equality holds. Now notice, this is really just beta over 1 plus alpha. So xn plus 1 is equal to beta over 1 plus alpha, which means we're going to be replacing beta over 1 plus alpha with xn plus 1. And we'll replace alpha plus beta I with this. Just realized maybe I shouldn't erase it just yet. But now, we're going to re-express the right-hand side in rectangular form. So let's just multiply both the numerator and denominator by 1 plus I xn plus 1. And if we expand out the numerator, we get this. And if we expand out the denominator, we're going to get this. So now we just group together the real part and the imaginary part. And we get this. So now we have this complex number is equal to this complex number. So we just set the real parts and the imaginary parts equal to each other. And so, by working with complex numbers, we didn't just end up figuring out one equality that is true, but we ended up figuring out two equalities that are true. In fact, we could take this further. So at this point, we were still considering an arbitrary real number x, an arbitrary integer n greater than or equal to 0. We know that these two equalities are true. Well, if we combine these two equalities together, well, let me first write out this equality. And let me just rewrite this guy in a different way, because that is really what we're doing. But we can replace the parentheses with this guy. So we have that this guy is equal to this guy. And if we multiply 1 plus xn plus 1 squared on both sides, they'll go away. And we're left with 2xn plus 1 is equal to xn times 1 minus xn plus 1 squared. And now, we would like to divide 1 minus xn plus 1 squared to the other side. But can we do that? How do we know that 1 minus xn plus 1 squared is non-zero? Well, we know that 1 minus xn plus 1 squared is non-zero because that's exactly what this equality is telling us, right? We know that the left-hand side of this equality is bigger than 0. So there's no way that 1 minus xn plus 1 squared could be equal to 0, right? So we can safely divide 1 minus xn plus 1 squared to the other side, and we get this. So this equality is also true. So we just said that 1 minus xn plus 1 squared is non-zero, which is equivalent to saying xn plus 1 squared is not equal to 1. In fact, we can show xn plus 1 squared is less than 1. Right, that follows easily from this. So if we just multiply 1 plus xn plus 1 squared to the other side, we have this. But the numerator is bigger than 0, the denominator is bigger than 0. So this guy is bigger than 0. So if we add xn plus 1 squared to the other side, we get xn plus 1 squared is less than 1. Okay, so now we have plenty of information to prove the behavior of this sequence, right? The claim is, if x is greater than 0, then this sequence is an increasing sequence. So how do we prove that? Well, let's first suppose x is greater than 0. And to show that this sequence is an increasing sequence, we want to show for all n, the nth term of this sequence is less than the n plus 1th term of this sequence. So let's consider an arbitrary integer n greater than or equal to 0, and let's write out the nth term of this sequence. So, what can we do with this? Well, we know that xn over square root of 1 plus xn squared is equal to this. Right? But then 2 to the n times 2 gives us 2 to the n plus 1. But now, the claim is, if we replace 1 plus xn plus 1 squared with its square root, it only makes the quantity bigger. Right? And the reason why that happens is because we know 1 plus xn plus 1 squared is bigger than 1. Therefore, the square root of this guy must also be bigger than 1, and in fact, it must lie between 1 and 1 plus xn plus 1 squared. Right? But if we take the reciprocal of both of these guys, it'll flip the sign of the inequality. But remember, in the case x greater than 0, all of the xn's are greater than 0. So certainly 2 to the n plus 1, xn plus 1 is bigger than 0. So if we multiply that on both sides of this inequality, the sign of the inequality remains the same. So this is what we get. So this guy must be less than this guy. And that's it. We have that the nth term of this sequence is less than the n plus 1th term of this sequence. This shows that the sequence is an increasing sequence. In fact, a really similar argument will show if x is less than 0, then this sequence is a decreasing sequence. So what would that argument look like? Well, the only difference would be that we would have x is less than 0, and then it turns out instead of less than, it would be greater than. And we have that the sequence is a decreasing sequence in this case. Right? The only reason why it gets swapped here is because instead of all the xn's being bigger than 0, all of the xn's are now less than 0. And so when we multiply 2 to the n plus 1, xn plus 1 on both sides, well, this quantity is negative, and so it'll actually flip the sign of the inequality. That's why we get this. And now we're ready to prove the theorem. So to prove the theorem, we're trying to prove a statement about every positive real number. So let's give ourselves an arbitrary positive real number x. From here, we can consider this sequence, and we know that these two sequences are both going to converge to arctangent of x. This sequence is increasing to arctangent of x, while this sequence is decreasing to arctangent of x. So if we were to visualize this, what's happening is something like this. Remember, all the terms in these two sequences are positive. So if we consider the sequence that is increasing to arctangent of x, well, maybe it looks something like this. Right, so it starts here and increases to arctangent of x. While the sequence 2 to the n xn is decreasing to arctangent of x. So maybe it looks something like this. Right, so you can visualize the behavior that these two sequences have. In fact, we show that this sequence is strictly increasing and strictly decreasing. So that's what we mean by increasing and decreasing. But then, by the monotone convergence theorem, we know that since this sequence is strictly increasing to arctangent of x, it follows that every term of the sequence must be strictly less than arctangent of x. Similarly, since this sequence is strictly decreasing to arctangent of x, that tells us that every term of the sequence is strictly bigger than arctangent of x. Right? This must be true. So in particular, if we take n to be 0, we have that the n equals 0 term of this sequence is less than arctangent of x. And arctangent of x must be less than the n equals 0 term of this sequence. Right? But we know that x0 is equal to x. So the left-hand side is really just x over square root of 1 plus x squared. The right-hand side is just x. So we have precisely this inequality. And so this completes the proof. And actually, another result we can establish that is similar to this one is the following. If we take n to be 1, then arctangent of x is less than the n equals 1 term of this sequence, which must be less than the n equals 0 term, since this sequence is a strictly decreasing sequence. But then, again, this is just x over square root of 1 plus x squared is less than arctangent of x. But what is 2 to the 1 x1? Well, we know that x1 is equal to x over 1 plus square root of 1 plus x squared. So then we have twice that, right? Which is less than x. And so this is sort of a tighter inequality for arctangent of x. And so not only is this inequality going to be useful, but this inequality is also going to be useful. So, right? So this is true for all x greater than 0. So we have this. Now it turns out if x is less than 0, then the inequalities just get reversed. And to see that, well, what happens? Let's consider an arbitrary x less than 0. Well then, negative x is greater than 0. So this inequality applies to negative x. So we'll substitute everywhere we see x with negative x. Then we have but we know that negative x squared is just x squared. And I'm going to rewrite 2 times negative x as negative 2x. And we proved in a previous video that arctangent of negative x is equal to negative arctangent of x, right? Arctangent is an odd function. So we have this. And now all we have to do is multiply negative 1 through this chain of inequalities. And the inequalities will get reversed. And so this is what we get. And now, let's go to that discussion we had at the beginning of this video. Right? The 2 claims that we had. If x is greater than 0, then arctangent of x is greater than 0. If x is less than 0, then arctangent of x is less than 0. Right? These 2 facts immediately follow from what we just proved. Right? So, proof. Suppose x is greater than 0. Well then, arctangent of x is greater than x over square root of 1 plus x squared. But x is greater than 0, and square root of 1 plus x squared is greater than 0. So this is greater than 0. And now, for the second claim, let's suppose x is less than 0. Then, we look at the blue inequalities. We have arctangent of x is less than x over square root of 1 plus x squared. But x is less than 0, and square root of 1 plus x squared is greater than 0, so this quantity must be less than 0. And so, this proves the two claims, right? They're really just corollaries of this result. And so, yeah, that's pretty much it for this video.